My name is Mickey Zhang, and I'm a software engineer at Microsoft. I work on the Azure machine learning platform, and my team deals with anything data related when it comes to the machine learning training jobs. And today I will be giving a talk on doing deep learning at scale on the cloud. So my talk today will be about deep learning in the cloud at scale, and it's mostly related to a data orchestration story. And in this presentation, I will talk about how Alluxio can enhance data orchestration and improve deep learning workflows. This is a collaborated effort with my colleagues Chao, Tianjun, and Bing from Alluxio. Here we have a brief overview of the talk. First, I will talk about the machine learning platform, what end-to-end lifecycle looks like, and what a typical data science workflow looks like. Then I'll talk about deep learning, as well as the additional challenges with deep learning. Finally, I will talk about where Alluxio comes in and how we leverage it for performance gains. First, the flowchart on this page shows a typical machine learning workflow, from processing input data all the way to developing a fully trained model. Typically, it involves data engineers who massage the data scientists who build the model, and DevOps engineer who build and deploy the model to the service. Azure machine learning platforms help streamline this whole process, providing a platform for all skill levels, empowering 1 million experiments per month. Now we have a graph that shows the iterative approach to build and improve a machine learning model. Our machine learning ops ensure models are reproducible, easy to validate and deploy. And now I will talk a little bit more about doing deep learning on the platform. So, deep learning excels at identifying patterns in unstructured data, such as images, sound, video, and text. For this reason, deep learning is rapidly transforming many industries, including healthcare, energy, finance, and transportation, and many more. At the same time, because of the nature of a deep learning algorithm, it requires large amounts of training data to make predictions. It depends on high-end machines and usually takes a long time to train the model because it has many layers. When it comes to deep learning, there are two models to do the distributed training. We want to parallelize the workflow as much as possible. And to do this, we can do it either through data parallelism or model parallelism. In the data parallelism approach, the data is divided into partitions, where the number of partitions is equal to the number of worker nodes. And inside this compute cluster, the model is copied in each of these worker nodes. Each worker will operate on its own subset of data, and keep in mind that each node has to have the capacity to support the model that's being trained. That is the model that has entirely to fit on each of the nodes. Each node will independently compute the errors between its predictions for its training sample and the labeled outputs. In turn, each node updates its model based on the errors and must communicate with each other, with all the changes with each other to update their corresponding model. This means that the worker nodes need to synchronize the model parameters and gradients, and at the end of the batch, they will ensure that the model is still consistent. Next, we have the model parallelism model. For model parallelism, the model is segmented into different parts that can run concurrently in different nodes. Each node will run the same data. The scalability of this model depends on the degree of task parallelization of the algorithm itself. And it is a more complex way to implement than data parallelism, as now you're dividing the model between the nodes. In model parallelism, worker nodes only need to synchronize the shared parameters, usually once for each forward or backward propagation step. Also, larger models aren't a concern in this case, since each node operates a subsection of the model on the same training data. For these two models, they are both cases of distributed training. And with distributed training, it comes with many challenges. We'll focus on the challenge of accessing and distributing the vast amount of training data. We use Kubernetes cluster to achieve the high degree of parallelism required for deep learning. For us, there are three typical deep learning scenarios categorized by input data type. First, there is Imagenet. It is a large amount of small files. And then there is BERT large. It is a medium amount of files, and all of the files are medium-sized. And lastly, for all deep learning scenarios, there will be a checkpoint, read and write. This is needed because the training jobs can fail or they can be paused to make the resources available for other more important workflows. And with the checkpoints, it would ensure a job can recover from failure or from the pause state and continue so that the work is not lost. In our current data consumption model, the training data is located in a centralized location, such as the NFS storage. During the deep learning job, all the worker nodes will fetch data from this location, and this could potentially lead to a data access bottleneck, especially when the numbers of worker nodes becomes large. So why do we use Alluxio? First up, performance gains. Alluxio provides local caching of training data. This is particularly useful as the data is remote from the computation in a cloud storage environment. Since Alluxio can cache data locally, the network I/O is only incurred within the compute cluster for accessing the data. And this in turn improves the data throughput and translate to less time for training. We will prefetch the data from the cloud storage environment so that during the data loading time, the cluster and the GPU resources can still be utilized by other process running the training job. And Alluxio is also flexible. It provides a unified namespace, allowing many different cloud storage sources, such as different storage accounts or even different cloud storage provider, to be mounted in the same namespace. Alluxio also includes a fuse interface for a convenient and familiar use experience. With Alluxio fuse, an Alluxio instance can be mounted to the local file system so that from the user perspective, interacting with Alluxio is as simple as interacting with local files and directories. This ensures that the user can continue to use familiar tools and familiar file layouts to interact with their data. Alluxio also helps with lowering cost. It is co-located in the same cluster and leverages the CPU, memory, and VM storage directly on the training cluster. This allows us to deploy Alluxio without the need to provision additional resources dedicated to hosting Alluxio service. And finally, Alluxio is scalable. It can grow and shrink based on the cluster size and job requirements. In the Alluxio sidecar model, we are now deploying Alluxio as a daemon set in our cluster, where there is one dedicated VM node to serve as Alluxio master. This is needed because Alluxio master generally consumes more resources when it handles the file I/O operations. And we want to ensure that it will be given enough bandwidth and computational power so that it can behave and work as expected. The Alluxio containers on the worker nodes will consume some CPU, memory, and storage resources within the training nodes. We are able to achieve this because all of the deep learning training jobs are very GPU intensive, and thus the CPU and other resources are mostly unutilized for the most of the training job, so that we can leverage the same resources and have it help to load and cache some of the data. And with Alluxio, our training data is prefetched and loaded into the Alluxio cache, which is on the node SSD. And this is distributed across the worker nodes. With training data preloaded, they can be fetched within the cluster without incurring remote I/O to the cloud storage accounts. This directly translates to a higher data I/O throughput, and thus results in higher GPU utilization during training jobs, leading to faster training time. Now, I will share some performance comparison for the aforementioned deep learning scenarios. And keep in mind that in every case, the training data is preloaded in Alluxio cache prior to performing the training. First, we have the Imagenet model. This is the many small files cases. And here we are testing with a standard PyTorch ResNet 50 training model. The data set we're testing with has about 1.3 million files, and all the files are between 50 and 200 kilobytes. We can see that there are two performance chart comparisons, and we notice that the training numbers, the performance can vary quite large depending on the training job parameters. And here I have chosen to show one where the batch size is 128 and where the batch size is 256. The measure for the comparison is image per second, and that's in the y-axis. And the x-axis shows the number of GPUs used in each case. And we can see that for both cases, despite the performance difference, we can see that Alluxio with data preloaded performs better than the NFS case. And especially for the batch size 256 case, we can see that while NFS does see some performance gains when we increase the number of GPUs, the gain sort of hits a ceiling. Whereas for Alluxio, as we increase the number of nodes and GPUs, the performance scales accordingly. Next, we have the Flowchart training case. For this pattern, we have about 100 different data partitions. Each of the data partition is about 1.8 gigabyte in size for an overall size of around 180 gigabytes. And here we can see the training time is on par between Alluxio and NFS when 64 GPUs are used. And when we double the number of GPUs with the NFS as baseline, Alluxio performs 20% faster. And on the right, we can see that for data partition access times, we see that Alluxio clearly is the winner here with its lower data access time per partition. We notice that after the first 100 partitions, the access time significantly drops for both the NFS case as well as the Alluxio case. This is because that after the whole 100 partitions are loaded into the training job, the data partitions are actually cached on the training container. And so that accessing subsequently the same data, the job can fetch that from the kernel cache and reduces the time required to access the partitions significantly. But that data is not a representation of the general data access speeds. And finally, For the checkpoint save and load case, we have a single file, a single checkpoint that is about 4.7 gigabytes. And the writing of this checkpoint is only done by the rank 0 process. And when we want to load the checkpoint, it is loaded by all the training processes. In this case, 24 of them. And on the right, we can see in the checkpoint write time, Alluxio is 3x faster than the typical NFS write time. And for loading, it is also much faster at 20 seconds compared to 100 seconds. Having a faster data loading checkpoint speed is very important, as all the nodes need to finish reading the checkpoint before the training job can start. So essentially, during the read speed, the entire worker nodes, all the cluster, is waiting for that to complete before a training job can be continued. Finally, the initial findings look very promising. We would like to bring what we have done to the production environment. And to do that, we will work with some select customers in a pilot program to see some real-world numbers. Further, we would like to continue to perform the Alluxio cache performance in our cluster. For example, cache localization is one of the areas that we're actively looking into. For cache localization, what we want is that during the data loading time, we want to put the data that will be consumed by the node directly on that same node. Currently, with the implementation approach, the data will be randomly distributed across the worker nodes. And when we access the data, we will either find the data on our machine, on the current node, or it will be on a different node within the compute cluster. This is a significant improvement from having to fetch directly from the cloud storage, but this can be further improved if we don't have to use the within cluster IO operation and instead to have the data on the disk themselves. If we can achieve that, we can expect to see further improvements when it comes to data throughput. In some preliminary experiments, we see that if we can access the data locally on the same node, then we can see about a 10x performance compared to having to fetch from within the cluster on a different node. And another area that we are looking at is actually user experience. Currently, during the data loading time, we have no way to see how we are loading the data and how much data is left. And this can lead to a little bit of uncertainty for the customer in that they have no way to see how much longer the data loading and fetching will be. So we want to create a progress indicator to show that with clarity, the process of preloading the data. And at the same time, we would like to have auto have failed. With that, I'd like to thank you for attending this talk, and I'll be happy to answer any questions. Thank you.